Alright, alright. So, hello, I'm Praveen Jagan, and I'm from New York State, and I came here for 2 weeks. And before coming here, what's, can we start? Alright, give me a sec. Alright. Hello, I'm Praveen Jagan, and I came here from New York State. I had just graduated 12th grade, and I'm going to college at Stony Brook University for computer science. Before coming here, I knew basic Python and like what it was. I knew how to do like some basic code. Like I knew basic functions like print. I knew type, and I knew the different data types, but I didn't know any libraries, and I didn't know data science. So coming here, I came to learn that. So today, I'm going to be talking about what I learned. I learned about pandas, visualization, linear regression, and logistic regression. The last two are machine learning. So, so pandas. So pandas is used for data frames. What I learned is basically a data frame is just what do you call it? A spreadsheet. It's the same. It's just that same type of idea. It has columns and rows. So what is a data frame? It's the table of data. And using pandas, we can modify these data frames so that we could better use the data and compile the data. So first thing when we have like a data frame is you have to convert it. Usually the data is in a CSV file, a comma separated value file. So first thing we have to do is convert this into a data frame. So what we do is we do pd.read CSV, and inside the quotations we put the CSV file and its location. So this converts the CSV file into a data frame. So in data frames, there's different types. There's some of the same types and some different types compared to just regular Python. This is a chart showing it. There's integers, which are just integer numbers, which are just numbers with no decimal point. But then there's also floats, which are floating point numbers, which do have a decimal point. However, then there's objects compared to just regular Python, which they call them strings. These are called objects in data frames. And there's Boolean values, which are true and false. But another thing I learned is datetime, which is a data type that is used to store dates and times, as the name implies, which is actually useful when when converting like a spreadsheet. So if you have like all the dates and times in like a different format, it converts it to a standardized format that you could easily use to like get the data out of it. So I can easily get what year it's from, what month it's from, and or what time it's from. So understanding the types of data. So to understand the types of data, there's dot describe, which tells us a lot of like the statistics of numerical data in these data frames. So it will tell us it will tell us like the mean, the standard deviation, like the different percentiles. All right, then there's also D types, dot D types, which tells us the data types of each column in the data frame. So if one has different types of data types, it will be classified as objects. And this is correlates to what I said in the last slide. So if we have not like NAs, like non-numbers, not a number or just a missing value, a blank in our data, this causes a lot of issues later on. So to find these, we could use dot is NA, which gives us a Boolean value for each data, each point of data, if it is an NA or if it's not an NA. And then if we use dot sum afterwards, it adds up all of those Boolean values to tell us the count of how many NA values there are. This is useful because if we know the amount of NA values, we can tell what we were going to do with that that column of data. Because if it's mostly NA values, we might as well just get rid of that column because it's not going to be telling us anything. However, if it's only just like two rows which have NA values, we can just get rid of those rows and use the rest of the data. So you like I said, you can get rid of the rows using drop NA, which you could either drop a row or drop a column. But then there's all which I just explained. But then there's also fill NA, which we can use to fill these NA values with the mean of all the other values, or we can use a median depending on what type of average we want to use. So to find values inside a data frame, there's two things. First, I'm going to talk about LOC, which stands for location. It uses the values like location using a row and a column. So usually the columns are name stuff. So this uses the name of the column. And usually the rows are just numbers, but they also can have names. So it uses the name of the row and the name of the column. So the row is most commonly still a number, but so it helps us find the value at that specific point. Then there's ILOC, which is index location or integer. But it basically tells us the location using the index instead of the actual name of the column. So you would give it two numbers and it would tell you the point, the value at that area of the data frame. So to organize data, we can use the group by function, which groups all values in the same, like with the all values in a column together. And then you have to have a modifier like mean sum at the end. So let's just say we have a data frame full of different items, and how much, if we have a data frame full of for a bake sale, and we have the amount of cookies we sold, but each cookie is classified as a different type. So we have chocolate chip cookies, sugar cookies, and we just want to know the amount of cookies we sold in total. We can use .group by and then .sum afterwards to find out the total amount of cookies we sold. And we can use like sort values, which can sort values in ascending or descending order. So if we have a bunch of values and we want to see which value sold the most, like which type of cookies in the same example sold the most, we can use descending to see the most sold cookies, and then we can use ascending to see the least sold. So visualization. So this uses two libraries. It uses pandas as well, but then it uses matplotlib and Seaborn. So needs to have like a complete data frame. So we can't have like NAs because that'll just mess up our visualization. So some data needs to be like in a specific format, which we can use pandas and the previous functions I described to do that. So a bar graph, we probably all know what a bar graph is. It is used to compare values of different categories. And the x-axis is categorical. So as you can see in this bar graph, you can see there's 4 categories, and they each have a different y value. And the function that we use is dataframe.plot, and then inside we put the kind as equal to bar. So then histograms. A histogram is similar to a bar graph, but it's used to visualize the distribution of a numerical value. So it's used to just see how data is spread out. And this is useful because we could see if there's a skew in the data. So we could see, oh, there's a lot more of the higher values than the lower values. So this is a histogram. As you can see, it's similar to the bar graph, but this compares a numerical value and then the count in that numerical value. So this uses the matplots, and it is used as plt.hist, and then you have the data frame, comma, the amount of bins. The bins is specifically the amount of different boxes we have there. So if we have more bins, it'll show more boxes. And if we have less bins, it'll show less boxes. The more bins we have, like the better shape we get, but the less the less you can like see the total like as the data as a whole, because it'll show just a specific line for each. So the counts might go really low, and you might have some with 0 counts, which kind of just meshes up the visualization. So this one has 20. So a box plot shows distribution, median, outliers in its like for numeric data. So this is useful because we can identify outliers. And it's used to compare the spread of values for different data. So for this, we could see the different categories. And for category 2, if we look at it, we see that there's these circles here. These circles are here to show that there's outliers in this, and they fell out of the range. And then for this, we use the Seaborn's library. So we use sns.boxplot, and then we put the data as equal to a data frame. So then a scatter plot. So then a scatter plot shows how different groups relate to 2 different numeric variables. And this is good to find correlation and patterns. So this is a scatter plot that shows 3 different categories. And as you can see like the blue category, it has a smaller on the X and a larger on the Y. And then there's a pattern to that. they're mostly all in that area. However, you can see at the bottom there's an outlier for it, which is useful just to know. And for this one, we use Seaborn as well, and we have the scatter plot where we have the x as an x value, the y as a y value, and the hue as the category. So the different colors are the different categories, and then the data is equal to data frame. Then we also have a heat map. A heat map is actually very useful in like machine learning, and it's a grid of data used to show a correlation between factors. So this shows the correlation between many different factors, so it makes it more easy to understand. So if we have a heat map like this, we have the different categories on the x and the y, and you can see there's a diagonal of 1. That's showing that category 1 has 100% correlation with category 1. So that's that just makes sense, because if it's the same data, it's going to have 100% correlation. However, you could see category 1 has a weak negative correlation with category 2 because it's a negative number and it's a small number. However, category 3 and category 4 have a strong positive correlation because that's 0.96, and the color is there to just help you visualize it. And for this, we also use Seaborns, and we use SNS heat map, and then we use data. And the dot correlation is because heat maps are most commonly used for correlation. You can use them for different things, but we are using dot correlation to show the correlation. And the NR is true is equal, just so that it shows the numbers in the box. So then now we're going to go on to machine learning. So there's 3 types of machine learning. First is supervised. Supervised has a dependent and independent variables. It's used to predict the dependent variables by the independent variables that we have. Then there's unsupervised, which is uses only independent variables. So there's only x's, no y's, and this is used to classify group data into different groups. And then finally, there's reinforcement, which is trial and error, and it guesses a score and then uses reinforcement to see if that's a good score or a bad score, and then it tries a new guess using from that. So then linear regression. Linear regression is supervised machine learning. So it does have an x and a y variable. So it has dependent and independent variables. So it uses the equation y equals mx plus b or y equals mx plus c. I like to use y equals mx plus b. The y is the dependent variable. The m is the slope. The x is the independent variable, and the y is the intercept. I've learned this already in math class, but to use this in machine learning was nice. So there's 2 types of linear regression. There's simple, where there's one independent variable. However, there's also multiple, which there's multiple independent variables. So multiple mx's. So the m, and in this, the equation, the m is turned into like a b with a number, and then the x is just x with a number, depending on the amount of variables that there are. So it uses pandas, matplots, sklearn, and from sklearn we import linear regression to help us with our linear regression. So first we have to train and test data. So there's 2 different groups. There's trained data and then there's test data. So we take all the data in the data frame and we split it into these 2 groups. We use the majority of the data to train the model. So we use it to create this model, this linear regression, this line, to help us predict data. Usually we use 80% of the data to train. Then we use the rest of the data to test the model to see if the model with the rest of our data accurately predicts the rest of our data. And we usually use the remaining 20%. This is done so that we could test like the effectiveness of our model using our data set. So because if we use just 100% of the data to train it, then that would be accurate, would most commonly be accurate with its data, with the model that it's predicting, because it's just using data that's been given. However, if we use data that hasn't been given to test it, where we know both values, we can see how good at it is at predicting new values. So first we have to create a model where we just have the model equals linear regression, and then we have to fit the model use to the data by using dot fit, and I just have the x train and the y train data. So if we have an independent variable that's full of, so sometimes we might come into some issues before we can fit the data. So if we have an independent variable that's full of strings and not numbers, we can use pd_get_dummies, because if it's a column that's full of, like, let's just say the string bad, good, or okay, we can't just put that into our dot fit because it doesn't know how to correlate these numbers. So what PD get dummies does is it creates a new column for each of these different strings, and it gives a 0 or 1 value so that so if it has the value or not. So let me just continue with this good bad okay example. If it would create a good bad okay new columns, and if the first one was good, it would have a one in the would have a one for the good, and then a 0 for the next two. But then it would just create three different columns, each saying yes or no to if there's a call if it's true or false. And yeah. So then there's variance inflation factor, VIF. This is the correlation between the independent variable and the other independent variables. So this checks how each um independent variable is with compared to other independent how dependent each independent variable is on other independent variables. So if we have a VIF of over 5, that means we have to get rid of we get rid of this column of independent variables because that shows that it's completely dependent on other independent variables. And so we remove that independent variable. So we also want our data to all be weighted equally in our model. So if we have like a column that ranges from 50 to 100 and a column that ranges from 5 to 10, the weight for the 50 to 100 is bigger because 50 is just a bigger number than 5. And we don't want like a model to say that this column is more important than another column. So we use standard scaler to standardize all the scores so that they're weighted evenly in our model. So this is the equation that standard scaler uses, and it takes the actual value, the mean of the column, and then the standard deviation to get a new value. So to test our model, we use dot score, and we use the test data instead of the train data this time. And this uses R squared to evaluate the effectiveness of our model. And it gives us a score from 0 to 1, and the closer to 1, the better the score is. And this is the equation for R squared, where we have the summation of the actual Y value, the summation of all the Y values minus the predicted Y value squared over the summation of the actual Y value divided minus the average actual Y value squared. And all that, and then you take one and you subtract all that from it. Then we have overfitting and underfitting. So sometimes we might overfit the data, and that's when the train accuracy is way higher than the test accuracy. And this model follows too closely with our training data. And it follows the trained data exactly instead of following the trend of the data. Then we have underfitting, which the trained data is has a way less accuracy than test data. This shows that it's too simple of a model and it fails to capture the trend of the data. So to fix overfitting and underfitting, we have to use regularization. And there's three types of regularization. There's lasso, ridge, and elastic net. And this fixes our problem with overfitting and underfitting. And then finally, now that we have a model that is good because we fix all these issues, we can use dot predict to predict the model. So we can use dot predict, and then it would just be a new x value, and it will give us a predicted y value. So then we have logistic regression. This is also under supervised machine learning. This is a classification algorithm, and this is used to predict binary outcome. So a binary outcome has two distinct values. So it's a yes or no, or pass or fail. So this uses the sigmoid function compared to the regular y equals mx plus b function that we use for linear regression. This is y equals 1 over 1 plus e to the negative x. This is the graph of the function. As you could see, it's bound by 0 and 1. So it'll never go below 0 and never go above 1. This is really good for us because this helps us with logistic regression because we want a predicted value to be only a 0 or a 1. So with this, we have a confusion matrix where we have where after we train a model and fit the model, we can use these values to find accuracy. The values are true positive, true negative, false negative, and false positive. And the true positive is when your predicted value is true, and the actual value is true. So if a model says yes and the actual data says yes. True negative is when they both are negative. A false negative is when we predict that it'll be negative, but it's actually positive. And and a false positive is that we predict that it'll be positive, but it's actually negative. So then we can use this to find accuracy, precision, the F1 score, the true positive rate, which is also known as VCOL, and the false positive rate. And then we have ROC, which is receiver operating characteristic, and AUC, which is area under curve. So the ROC is used to graph the threshold value, which is just a value that if the value is above, then it says yes, and if its value give is below it, it would say no to. A model would say no. This compares the true positive rates and the false positive rates for different thresholds. Oh. All right, so this is a diagram that shows the ROC and the AUC. The ROC is the actual curve, and it shows these threshold values. And the area under curve is just the area under the curve, and it's used to determine how good this model is. So the bigger the area under the curve, the better the model is, because that shows that there's more true positive rates and less false positive rates. And the larger the area under curve, the better the model. So that's it for my presentation of what I learned. Thank you. Yeah, any questions?